I'm Sophie Rosenfeld, project director for this year and a member of the history department here at Penn. And this afternoon, it's my distinct pleasure to welcome a colleague from across the university, Michael Kearns, to our series. Michael's a distinguished professor in Penn's computer science department, where he holds the National Center Chair, and is the founding director of the Warren Center for Network and Data Science. Michael also has appointments in the economics department and in multiple departments at the Wharton School, which should give you some idea of his breadth, and he consults widely in the world of finance and technology. But what makes Professor Kearns so unusual and a wonderful addition to this series is not just his renown as a computer scientist, it's also his thoughtfulness about the social and ethical implications of his areas of expertise: machine learning, artificial intelligence, and especially algorithmic decision-making, and his ability to explain developments in those fields to those outside the technology sector as well as within. We invite him here today to tell all of us across areas of interest, professions, schools, knowledge levels, something about where we are now when it comes to artificial intelligence and algorithmic design, where we're headed, the challenges before us, and what we can do about them. I think we're all at least vaguely aware of how much algorithms shape our daily lives these days, from medical care to the picking of movies to watch, helping us ideally make better decisions. But we're often less aware of some of the negative impacts of these developments, including on justice and fairness. And Professor Kearns neither brushes away the problems, nor does he suggest we give up on artificial intelligence. Instead, he's focused on how algorithms themselves might be made better and indeed more ethical, an idea with enormous implications for the future of choice making. So Michael's going to speak now for about 40 minutes on the ethical algorithm and the future of choice, which is also the subject of his 2019 book, co-authored with Aaron Roth, called The Ethical Algorithm: The Science of Socially Aware Algorithm Design, which I recommend to all of you as a complement to this evening's lecture. Then he'll take some questions from the audience. So please listen, think, write your questions into the Q&A at any point, and we'll take up as many of them as time allows. Thank you very much.
Sophia, thank you very much for the introduction. Thanks to all of you for joining me here. So I am first and foremost a career machine learning researcher, as we would call it. I've been working in the field since graduate school in the late 80s. So suffice to say, I've seen a lot of change in my career. When I was working on it in graduate school, machine learning was an obscure corner of the then discredited field of artificial intelligence. And so I've seen a lot of change, especially in the last 10 years. And those of you who follow technology news will know that, especially in the early part of this decade, there was quite a bit of excitement around, kind of major empirical successes of AI and machine learning in areas like computer vision and speech recognition. And these products and services now, this technology now, is stuff that we all use daily. It's embedded in the apps we use, the technology we use. It's almost like electricity now, in the sense that we don't even notice it. We expect it to be there. But those of you who also follow technology news might know that the last 5 years have seen quite a bit of buzzkill in the sense of kind of collateral damages or unintended side effects of AI and machine learning, especially in consequential domains where AI and machine learning are used at scale, like consumer lending or criminal sentencing, and similar areas where algorithms, and more precisely predictive models trained by machine learning and AI, are routinely making extremely consequential decisions about individual citizens. And there's been a lot written about this. There's a lot written about it every day now in even mainstream media outlets. And there's also been a lot of very nice books written for general audiences that treat these topics. I've shown you the covers of a few of them here. Many of you might be familiar with Weapons of Math Destruction, which was the focus of the Penn Reading Project a few years back. And just to be clear at the outset, my friend and co-author Aaron and I, we like all of these books, and we think they serve a very valuable purpose. And where we felt they were a bit lacking, and the area in which, in some sense, our book is a response, is when you get to the solutions sections, so to speak. And in these books, most of these solution sections comes towards the end, where after the problems have been viscerally laid out and illustrated, the author says, okay, so what should we do about all this? And the answers are, generally calls for better laws, better regulations, watchdog groups. We need to keep an eye on all these problems. And we agree with all of that. But as scientists working in the fields in question, we also know that algorithms and the models produced by areas like machine learning and AI are designed, engineered human artifacts. And if there's something we don't like about the behavior of those algorithms, we could think about fixing the algorithms in the first place, rather than waiting for the harms to happen and then, for instance, legislating or regulating after the fact. And, there wouldn't be much more to say about this if, in fact, there weren't a very large community of scientists in these fields who have been actively working on doing exactly that for roughly 5 to 15 years. And so our book is really a general audience, or it's intended to be a general audience kind of science book about designing algorithms that are better behaved from a social standpoint. And just to kind of lay out what the scientific agenda I'm talking about is up front, we are talking about a research agenda that seeks to literally embed social values in algorithms. So I really mean like writing Python code that somehow encodes or enforces notions of things that we think of as social values like privacy or fairness, or maybe even things like morality. And I say here a modest proposal with a question mark for two reasons. One is that in many ways, scientifically, this is not a modest agenda, but I also am aware that people outside of the area of technology might also find this proposal creepy in the Swiftian sense of a modest proposal. But what I'm hoping to convince you in the time I have here today is that this is something we know a little bit about now. It's still very, very early days. There's many things we don't know. And in many ways, I don't think there's anything creepy about it. In fact, I think it is necessary in the technological and algorithmic era that we live in. And maybe the first thing to say about this agenda of encoding fairness in a machine learning training algorithm in your Python program is that, of course, if you're going to explain something to a computer, you need to be exceedingly precise about exactly what you mean. And I don't think it'll be lost, especially on this audience, that computer scientists and machine learning researchers are far from the first community of scholars to think hard about things like fairness, for example. Of course, interest in that topic goes all the way back to the Greek philosophers, and more recently, for at least 100 years, economists and legal scholars have thought very carefully about what fairness means, what are different notions of fairness and the like. But none of those communities have ever had the interest or the need to be so precise about what they meant by those words that you could actually write it down in lines of computer code. And one of the things I hope to convince you of here today is that in addition to that being a necessary prerequisite for the scientific agenda I'm going to describe here, sometimes thinking that hard about what you mean by a word reveals flaws in your intuitions about that notion that you weren't going to discover any other way. And it's not enough to just be precise. In fact, I'm going to give at least 2 examples today where society has sort of tried to be precise about what is meant by something like privacy and fairness. And in the view of my co-author and I, got it exactly wrong. So it's possible to be precise and get it wrong. And so what I want to do today is just kind of spend some time illustrating, what this scientific agenda looks like, where we are roughly, what we know, what we don't know. And I'm going to kind of do it around mainly privacy and fairness. And I've listed a bunch of social norms on this particular slide. And the grayscale here is meant to indicate our subjective assessment of how mature each of these different areas is. So in particular, we think that the study of algorithmic privacy is perhaps the most mature of the areas in the scientific agenda that we describe in the book. Fairness is maybe a decade behind, but is off to a good start. Things like explainability and interpretability in AI and machine learning, which you may have heard or read about, we think are very important concepts, but we think the science isn't there yet, that there aren't even good proposals for what the definitions would look like. And just to make a brief comment about the theme of this series, I realized when I thought about what I was going to say here today and its relationship to the topic of this speaker series, is that in many ways our book is entirely about choices, and often very difficult choices. It's difficult choices of what the right definition of something like fairness is. It's about trade-offs within those definitions, what the relative merit of fairness versus predictive accuracy. In the case of fairness, often one has to choose what group or groups you want to protect and what harm you're trying to protect them from. In things like social media, we might have to make choices between things like engagement in the Facebook sense and civil discourse. And more generally, kind of overlaying all of this are hard choices about when and whether to make relatively technical solutions to problems or when to choose social solutions. And hopefully this will come out a little bit in the remarks I make today. Okay, so I'm going to basically spend most of my time just going through two little vignettes that are meant to give you a sense of where the science is and where the science isn't yet. And so I want to start off with talking about data privacy and more generally algorithmic privacy. So I think probably everybody here has some intuitive sense of what we mean by data privacy. It's about people not being able to access your private data if you don't want them to. And it's also about people not being able to make unwanted inferences about you from what's publicly available about you. And to give an example of a kind of precise definition or type of definition of privacy that gets it exactly wrong, I'm going to start by picking on the prevailing notion of privacy that appears in laws and regulations in the United States and around the world, which are notions of privacy based on anonymization, removal of so-called personally identifiable information, et cetera. So if you look in the United States, for instance, at HIPAA law, which governs medical care records, there are these 17 fields that must be eradicated from any data set before that data set is considered properly private or anonymized. And one of the interesting scientific developments in the last 20 years in the study of data privacy is the realization that these notions of privacy are fundamentally irretrievably broken. And so there's a famous quote from Cynthia Dwork, who's on the Harvard faculty and who is one of the founders of the considerably better or right notion of privacy I want to discuss in coming slides. And her quote is, "Anonymized data isn't." And what Cynthia means by that is either you've had to anonymize the data so much that it isn't really data anymore, it's not useful for anything, or you haven't anonymized it enough and therefore it isn't anonymized. And so let me just try to illustrate what the problem I have in mind is here. Suppose that over at Huff, which is like a quarter of a mile in this direction from me, well-meaning researchers there want to take a set of medical records and release it or share it with other researchers for the purposes of scientific research that we would all benefit from. Okay, and knowing that there are concerns with releasing or sharing medical records between hospitals, in this toy database at the top of the slide here, they've gone in and done some anonymization. So they've redacted certain columns entirely, like name, and they've coarsened other columns. For instance, age, rather than being given in the exact number of years, has been grouped into deciles. Gender is preserved, the last 2 digits of zip code have been redacted, etc. And the magical thinking around anonymization notions is that somehow if I do enough of this kind of deletion and coarsening, that there should be some privacy promises, right? But unfortunately, nobody, has ever precisely articulated the semantic notion of privacy that you should find satisfying that these kind of operations on the database would provide. And so the real problem with anonymization in a nutshell is that it pretends like the data set in front of you is the only data set that is ever going to exist now or in perpetuity. And if that was ever the case, which I doubt that it was, it is certainly not the case in our modern algorithmic era. And so the problem arises, for instance, when I happen to know some additional information about someone. So let's say I have a neighbor, her name is Rebecca, she's female, and I know she's 57 years old. And so I can go to this top database and, from the attributes I know, there's 2 records in this allegedly anonymized database that match my neighbor. And so somehow this should be a privacy guarantee because now I'm confused about which of these 2 records highlighted in red belong to my neighbor. Now notice that already from just these 2 records, I know that my neighbor is HIV or has colitis, which she might well consider a violation of her privacy already. But you might wish this away by saying like, well, there are 10,000 patients at HUP, and if I did enough of this, maybe there would be 100 records that match Rebecca, what I know about Rebecca, and then I'd really have ambiguity about her diagnosis. The real Achilles heel of anonymity is that it is sort of what's called triangulation or linkage attacks. So suppose that at the bottom is the hypothetical anonymized data set of Jefferson Hospital, and I happen to know that my neighbor Rebecca was also a patient there. And so, from the top database, there are 2 records that match Rebecca. On the bottom and allegedly anonymized database, there are 3. But by taking the intersection of these 2 databases, I now uniquely know that my neighbor has HIV. And this is not an academic concern. There have been many, many real world attacks on released anonymized data sets. The so-called Netflix prize from a decade ago was the first highly publicized such incident in which allegedly anonymized data sets were re-identified, as they say, with specific real world individuals matched to the records in the anonymized database. Okay, so anonymization is broken, even though this is the prevailing notion that you are told to appreciate from major technology companies. What's a better notion of privacy? Well, in the last 15 years, it has been proposed and largely agreed that a much better, in fact, I might even go so far as to say the right definition of privacy is what's known as differential privacy. And differential privacy, I'm going to give a very concrete example of it and somewhat amusing example of it on the next slide. But at a high level, the idea behind differential privacy is the following. If we take it as an axiom that a computation or analysis that is done that doesn't look at your private data at all cannot violate your privacy, and I propose that we should take that as an axiom, that if a computation or analysis doesn't even use your data, it can't possibly violate your privacy. What I want you to do is, let's imagine a computation or analysis that takes, a set of medical records, and one of them is your medical record. This is the highlighted medical record of Xavier in this cartoon here. And so we go ahead and run this analysis or algorithm, including your medical record highlighted in red, and we get a certain outcome or output from this analysis or algorithm. And I want to compare that to running the same algorithm or analysis with n-1 medical records where you are the -1. So, we're going to imagine running some algorithm on the entire data set of medical records at HUP, and then the same algorithm run with just your medical record removed. Although, of course, we're going to do this counterfactual unilateral removal for all 10,000 patients separately. And if we cannot distinguish the output of this algorithm or analysis, in the case when it did use your data as input versus when it didn't, then we can't tell the difference between the axiomatic case where your data wasn't touched at all and the case where it was. Then we should say that the one that did use your data as input also preserves your privacy. And there's many, and so this is the high level idea behind the definition of differential privacy. It's a very strong semantic guarantee of individual privacy. And it also, interestingly, requires that algorithms or analyses that meet this definition of differential privacy are randomized. It means they actually need to, kind of flip coins during the process of the analysis or computation. And that's because the way one achieves differential privacy is by adding noise to computations or data at particular points in particular ways. Okay, this is probably the most abstract thing I'm going to say in this talk. Let me now give a very concrete example of differential privacy. So interestingly, the first example of a differentially private algorithm, or what I might call it protocol, predates the definition of differential privacy by 40 years. And this is something called randomized response. Randomized response is a proposal from the kind of social science the kind of social survey literature in the 1960s. And it's a proposal for how to elicit collectively truthful answers to questions from a population in which one of the answers might be stigmatizing. So let's suppose, for example, that I want to survey the population of Philadelphia on the question of, have you deliberately violated social distancing guidelines during the pandemic? And let's say, for the sake of argument, that answering no to that has no social stigma, but answering yes does have a social stigma. So if we just perform this survey in a straightforward way and start asking people, even on an anonymized website, have you violated social distancing guidelines? We might expect a massive and uncontrolled underreporting of the yes answer. Okay, so what do we do instead? So in randomized response, I ask you to do the following thing. In the privacy of your own home, I want you to flip a coin, okay? If the coin comes up heads, which is this top branch, which happens with probability 1/2, then I want you to answer the question truthfully. Have you violated social distancing guidelines, yes or no? If, on the other hand, the coin comes up tails on this bottom branch, then I want you to flip the coin again. And if it comes up heads, I want you to answer yes, regardless of whether you violated social distancing guidelines or not. And if it comes up tails, I want you to answer no, regardless of what your truth is. Okay, so so first of all, this protocol meets the formal definition of differential privacy, which I'm not going to give you the formal definition because it's technical. But even without knowing what differential privacy is, one of the immediately obvious properties of this protocol is that anybody who answers yes has plausible deniability. So if I run this protocol and, Sophia answers yes to it, I can say, what, you violated social distancing guidelines deliberately? She can say, no, I haven't. Of course I haven't. I'm a responsible citizen, but I did what you asked me to. And the first coin came up tails and the second coin came up heads. So I said yes, because that's what your protocol asked me to do. And every single person in the population who answers yes simultaneously has this plausible deniability. But, a little bit of arithmetic that I'm not going to do reveals that if a large population faithfully follows this randomized protocol, I can still back out from those randomized answers an extremely accurate estimate of the true fraction of people that have violated social distancing guidelines. And this is exactly the two forces or choices, if you like, the differential privacy balances. On the one hand, we want to be able to compute kind of aggregate statistics or aggregate analyses. I don't really care if Sophia specifically violated social distancing guidelines. I want to know what the fraction of the population that did was. So any kind of computation that I want to do that's about an aggregate population, but I want to protect the privacy of specific people's data, this is what differential privacy is meant to provide. Okay, now differential privacy kind of spent the first 10 years of its existence in the laboratory, or more precisely, since this is computer science, on the whiteboard, but is now starting to see kind of meaningful and large-scale deployments, commercial and otherwise. So on the topic of COVID, for instance, back in the spring, Google started publishing what they called community mobility reports, which were basically heat maps showing you in your metropolitan area what areas of the city uncomfortably large numbers of people were gathering in uncomfortably close proximity for uncomfortably long periods of time, in case maybe you were one of those people and you wanted to stop doing that, or you wanted to know where to avoid. And how did they get the data for these heat maps? Of course, from the geolocation data on Android phones. And they are very aware of the fact that without any special effort, just releasing even these aggregate heat maps without sort of the randomization that differential privacy calls for, that might be subject to these kinds of attacks that anonymity is vulnerable to, where I kind of triangulate a bunch of these heat maps, perhaps over many days, and I figure out exactly where you've been on each day. And so they didn't just release the raw heat maps unaltered. They released differentially private versions of those heat maps. They basically added noise to those heat maps that still made them useful for the purposes of knowing where the hotspots were, but also gave some guarantees of individual privacy. And the real moonshot for differential privacy is going on even as we speak, because the US Census a few years ago decided that every single report and statistic that they released as a result of the raw block by block census count data in the 2020 census would be done under the constraint of differential privacy. And so that's great from a privacy perspective. As the randomized response example shows, right, providing that privacy comes at some expense to accuracy. And so one of the concerns about the use of differential privacy in the census is that when you add the noise to the counts of extremely small communities, which might be largely minority communities, for instance, in Alaska, you might actually disappear those communities by the addition of the noise. And since census data is used for federal budgeting decisions, this could have real economic consequences for those communities. And there's no fix to this. This is a hard choice. You want to provide more privacy, you need to add more noise, and you have to run the risk of a greater chance of disappearing some communities and affecting them economically. Okay, let me say a little bit about fairness now. So the study of algorithmic fairness compared to algorithmic privacy is much more of a work in progress. In particular, I've kind of suggested to you our opinion that differential privacy has been broadly adopted as, if not the right, a right definition of privacy. Not only do we not have that kind of consensus in the study of algorithmic fairness, there's a sense in which we know that won't be possible. So in just the last few years, there have been a number of papers that kind of take on the form of Arrow's impossibility theorem in social choice theory, for those of you that know about that. These papers start off by saying, like, well, why do we have so many definitions of fairness? Why don't we wrap these all up into one that has all of the good properties of these different definitions? And the paper then says, like, well, look, let's take an axiomatic approach. Here are three properties that we would want any fairness definition to meet, right? And you, the reader, you look at these three axioms and you say, yes, 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 these are extremely weak axioms. I would definitely want these three axioms to hold, but I probably want other things to hold too. And of course, the punchline of the paper is, well, guess what? Here is a theorem proving that you cannot simultaneously achieve these three properties, except in perhaps trivial, uninteresting, unrealistic situations. So not only in the study of fairness will there, again, as in differential privacy, be a trade-off between fairness and accuracy, you might really have different definitions of fairness fighting with each other. And just to make this, painfully clear, you might find yourself confronted with a data set in which asking for more fairness by race necessitates your accepting less fairness by gender. Okay, it doesn't have to be the case, but there are such data sets. Okay, so again, hard trade-offs are hard choices. But I want to spend, most of my remaining time just giving you some sense, since it seems like every day there's a new headline about this or that lending model, or this or that criminal recidivism prediction model, or this or that college admissions model having racial, gender, or other bias. I want to just sort of explain how this happens in layperson's term. Why does this happen? Is it, for instance, that machine learning engineers are incompetent, or worse, are racist and writing little lines into their code that say well, if the applicant is white, then do this, otherwise do that? The answer to that is more or less a resounding no. In some sense, the answer is more disturbing than that, because it turns out that the actual scientific principles of machine learning, if adopted unmodified, you should expect them to lead to different kinds of discrimination or bias. And I'm going to try to explain why in a few slides. So let's suppose that the Penn admissions office, which is only a couple hundred yards over this way, were to ask me to help them build a predictive model for success at Penn based on information from high school applicants to Penn. Okay, and to make things simple, let's suppose that, and so that I can draw pictures, let's suppose that we only have two attributes of a high school applicant that we're going to use to make this prediction. On the x-axis is the high school grade point average of the applicant, and on the y-axis is the SAT score. And so we have a cloud of green points here, okay? And the x coordinate corresponds to the GPA of that applicant, and the y-axis corresponds to the SAT score. And the pluses and minuses indicate whether that student succeeded at Penn. So immediately, just to be clear, I'm talking about a data set which has been filtered 2 times already, right? Because in order to know whether a student succeeded at Penn or not only did they have to apply, we had to accept them, and then they had to matriculate. They had to choose to come, okay? And there are all kinds of biases that could already be present in this cloud of points that I'm showing you because of those steps of filtering. But even wishing that problem away, let's suppose that somehow this is an unbiased set of students admitted to Penn who actually attended Penn. The pluses and minuses here are meant to indicate whether that student succeeded at Penn. That student then matriculated to Penn succeeded. And just to be concrete, for the definition of success, we can use any kind of quantifiable, objectively measurable outcome. Let's say, for the sake of argument, that it's graduated within 5 years of matriculating with at least a 3.0 GPA at Penn. Okay, so the pluses here indicate the students that met that definition of success, the minuses that indicate the ones that didn't. So even if you know nothing whatsoever about machine learning, and I showed you this cloud of points, which general, by the way, has the structure that you would kind of expect. The pluses tend to be up and to the right, higher GPAs and SAT scores. The minuses tend to be towards the lower left, but it's noisy. But even if you didn't know anything about machine learning and I asked you to eyeball this cloud of points and pick a predictive model, you might well predict this, what we would call a machine learning linear classifier, which just means you draw this line through the cloud of points, and anything above and to the right of this blue line, you're going to predict success. Anything below and to the left, you're going to predict non-success. And this model is quite accurate, right? It's not perfect. It makes some false positives. These are students that this model would have admitted that in fact did not succeed at Penn. And it makes some false negatives as well. These are these pluses down here, which are students that actually did succeed at Penn that this model would have rejected, okay? Now, suppose I told you that this cloud of data points was not the entire data set, that there was another subpopulation of the data, let's call them the orange points, and here they are. And there's a few things to notice about the orange points. One is that the oranges are a minority in the literal sense that there are far fewer orange points than green points. The other is that there seems to be something different about the distribution of these orange points compared to the green. In particular, the orange cloud of points seems to be shifted down on the y-axis, i.e. has systematically lower SAT scores than the green population. But despite that, they are not less qualified for success at Penn. If you had bothered to carefully count the green points, you would have discovered that slightly less than half of the green points were pluses, whereas in the oranges, it's exactly 50-50. So what's going on here, right? Why is it the case that the orange population is just or more qualified for success at Penn than the greens, even though their SAT scores are lower? Well, I might offer the following narrative. Suppose I told you that the green students were from a wealthy demographic. And because they're from a wealthy demographic, they have the time and money to pay for SAT preparation courses and multiple retakes of the exam, and then kind of super maxing their scores, all of which take time and money. And the orange population comes from a less wealthy demographic, and so is much more likely to be working a job outside of high school to support their family. And so they generally, do a bit of self-study on their own, take the exam once and take whatever score they get, okay? So what's the problem here? The problem arises, okay, and by the way, if I asked you to build a predictive model for just the orange population in isolation, you might well pick this purple linear classifier, which does a perfect job of separating plus from minus. So where does the problem come in? The problem comes in when I look at the combined data set and I ask, as is the normal ask in machine learning, to find the single predictive model which minimizes the error on the overall combined population of applicants. Well, it turns out that that model is exactly the same model that we would have chosen to minimize the error on the green population alone. Because just visually, you can see that if I try to move this blue line down far enough to accept these 5 orange pluses, I will pick up so many green minuses on the way that my overall error on the data set will increase significantly, okay? So the model that we're looking at here, this blue linear classifier, is the model that the standard principles of machine learning, which is mainly focused on just predictive accuracy, would naturally pick out. But now there is a quantitative sense in which we can actually measure the unfairness of this model. Because if in college admissions, I think of the greater harm as being a false rejection, we might also think of false acceptance as a harm, right? Because it's not great to be accepted to a college that you then don't succeed at. In the same way, it's not great to be given a loan that you can't repay. But if we, for instance, for the sake of concreteness, define our notion of unfairness to be the disparity in the false rejection rates between the orange and the green classifier, between the orange and green populations, this classifier, which minimizes the overall error, also is about as unfair as you can get, because the false rejection rate on the green population is close to 0, and on the orange population it's close to 100%. Now, you might be saying, well, this is stupid. Why don't I build a 2-part classifier? If the applicant is from the green population, then I apply the blue classifier, and if they're from the orange population, I apply the purple one, and this adjusts for this systematic difference in SAT scores, which is not directly related to success in college. Good idea. Unfortunately, to the extent that we have laws in the United States and elsewhere that are precise about what fairness means, this kind of 2-part model is explicitly forbidden. So for example, in the United States, in consumer lending, it is against the law to have either a process, model, or algorithm that uses race as an input in consumer lending decisions. This toy example I've given you is an example where such a law, while I'm sure well-meaning like definitions of anonymization for data privacy, gets it exactly wrong. Because on this example, that notion of fairness of forbidding looking at race or group here actually guarantees harm to the very group that you thought you were protecting by such a law. And so we argue in the book that definitions of fairness that try to get at fairness by restricting what inputs you give to a process or a model are broken. And that what you should do instead is explicitly constrain the output behavior of your model to not, for instance, discriminate in the way that the blue model does, okay? What would that look like? Well, that would look like just kind of a rather small technical modification to our objective, right? Rather than saying, let's find the model which minimizes the overall error, period, we could say, let's find the model that minimizes the overall error, subject to the condition that the difference in the false rejection rates between these two populations is at most, I don't know, 0%, 1%, 5%, 10%. So we have a knob in this definition. It's a quantitative or parameterized definition, as we would say in machine learning. In the theme of this series, there's a choice to be made here, right? Because if we set that knob at 0% and demand exact equality in the false rejection rates, that's a very strong constraint, and that might come at the cost of greater predictive error. If I turn that knob to allow 100% difference in the false rejection rates, then it's like I didn't ask for any fairness at all. And you can actually study quantitatively on real data sets where fairness is a real concern, exactly what this trade-off looks like. So if you look at this far left figure, for example, I know you can't read these axes easily, but on the x-axis is predictive error, so smaller is better. And on the y-axis is unfairness as measured, for instance, by something like the difference between the false rejection rates between the two populations on the cartoon before. And every one of these red dots corresponds to a different model. It's like a different way of drawing a line through the cloud of points on the last slides. And what you can see, of course, we'd like to be at zero. We'd like to be at the origin. We'd like to find models that have zero error and zero unfairness. In real machine learning applications, even ignoring fairness, you're usually not going to get to zero error, okay? But this curve shows us the choices we have, right? We can either choose to pick this model way up here, which has the smallest error and very large unfairness. Another choice is this model down here, which has zero unfairness, but high error. And in between, we get things in between. And the shape of the curve matters, and the numbers on these axes matter, and what's at stake matter. Like we might make very different choices about what point we picked on this curve. If I told you that this was a criminal recidivism prediction that's going to be used as input to somebody's sentencing, versus what's at stake here is what ads you get shown on Facebook. And just to make, I think, a very important point here, somebody like me can generate figures like this and explain what they mean, for instance, to the admissions office at Penn. Somebody like me shouldn't be deciding what the right trade-off between accuracy and fairness is. That should be done by people, who are the stakeholders, who know about the domain, who've thought deeply about, the relative balance of justice, if you like, or fairness between accuracy in overall predictions and some particular notion of fairness. Okay, I'm almost out of time and want to leave time for Q&A. But what I've described to you so far more or less covers the first half of the book that we wrote. And I want to point out something about everything I've said so far, which is I've implicitly been inviting all of you to think so far about as algorithms being the perpetrators of harm on innocent civilians or citizens, right? So it's like, you might be denied for a loan, your private data might be leaked by an algorithm, and you don't even know that that happened to you, and you don't even know that an algorithm was responsible, okay? there are a lot of settings in our modern world where it's not so easy to exclusively place the blame on the algorithm, because a population of users of an algorithm, or more precisely an app, are complicit in some feedback loop with the algorithm itself. So here, for instance, I'm showing you a screenshot from Google Maps, asking for the lowest driving time route between Penn and Longwood Gardens, okay? So, what could be better? Think, for those of you that are old enough, like I am, to the era of fold up maps in the glove compartment, and maybe, half-hourly traffic reports that only covered the main freeways and might well be stale by the time you got there. What could be better than this app where you say, I want to go from here to there, and in response, not just to what the map looks like, but to all of the real-time GPS traffic data on the roads right now, basically tells me this is the route which is your lowest driving time. What could be better? Well, this is where kind of game theory comes in, because what a game theorist would say these apps are doing is they are nudging us towards a selfish equilibrium, right? Because at a high level, driving on the roads, it is a game in the technical sense that where everybody else is driving affects the driving times that I experience, and where I drive affects all of your driving times, perhaps in a small way, but in the aggregate in a big way, okay? And so what these apps basically let us do is all compute in response to what the rest of you are doing right now, my selfish best option. And this basically is nudging us towards some kind of competitive equilibrium. For those of you that are familiar with it, literally a Nash equilibrium. And for those of you who know a little bit of game theory, you will know that just because something is an equilibrium doesn't mean all of us, or even any of us, are better off for it. And in particular, there's a famous theorem called that goes by the name of Brace's paradox that actually shows that in a network of roadways where we are all affecting each other's driving times, it could be the case that all of us are, by acting in this self-interested competitive way, all of us are actually driving roughly 33% more than we collectively needed to under some alternate centrally designed, I might even call it socialist solution, okay? And so you might say, okay, big deal, who cares? I'm still going to use these apps, even if collectively we might be worse off right now. For me to get from Penn to Longwood Gardens, it's going to be faster for me to use the app. And so again, kind of what's at stake matters. And I think we're all quite familiar with this level of personalization. Like, if you shop on Amazon, it's always making recommendations, maybe ones that you even like quite a bit, about what products or books you might be interested in. And so it's hard for me actually to argue that you're receiving highly personalized recommendations for products that you like somehow has a negative impact on me, the way it might in the sense of commuting, because we're kind of competing for a finite resource when we're driving on the roads. But I ask you to think about things like Facebook's news feed, right? Which is optimized for your engagement, right? So like Google Maps, the news feed algorithm of Facebook is just trying to give you what you love the most, right? Your shortest drive, instead of your shortest driving time, it's the content that you seem to most respond to. And your incentives are aligned with Facebook's, because the more time you spend on Facebook because you just love the stuff that it's feeding you, the more ad inventory they have to show you, and the more revenue that they make, okay? And so, you can ask, well, what's wrong with that? And again, I think it's quite useful to kind of separate the individual from the collective. From your perspective as an individual, maybe there's nothing wrong with Facebook optimizing the content you see for your interests, but maybe collectively things like that drive us to a bad equilibrium, in the sense of leading us to a collective state where we are more isolated and less tolerant of opposing viewpoints, and have a less deliberative democratic society. And I am far from the first person to kind of observe that perhaps we are in fact in such a bad equilibrium. And one of the things that we do in the book, kind of in keeping with the spirit of what are scientific solutions to these problems, is point out that I promise you that the same machine learning model that tells Facebook what content you love the most, that same model tells Facebook what content you hate the most. And so I will end with like the proposal that if Facebook wanted to, they could, they could play with the mixture of content they showed you and know, statistically at least, whether they were showing you a mix of stuff that you only loved, only hated, or in between. And there's no reason that they couldn't, in fact, give us all like a little slider that we could experiment with ourselves each day, asking for different mixtures of content that Facebook thinks we would like versus things that we wouldn't like. And so let me stop there, and hopefully I've left a little bit of time for questions, and thanks all of you for attending.
Thanks so much, Michael. That was extremely interesting. And not surprisingly, a number of questions have come in since. I have some of my own too, just because you've brought up so many terrific examples here. But I'll start with this one because it asks you something about the kind of cultural specificity in all of this. And it said, I'd be interested to know how cultural specificities are taken into account, if at all, in defining key terms such as privacy, since what is understood as desirable privacy may differ according to country, culture, or context, medical privacy versus, for instance, privacy in what I post on Instagram. That made me think too of the fact that, when I talk about these questions with my own students, they're certainly very interested in fairness, but they're not that interested in privacy. Privacy doesn't strike young people sometimes as quite as pressing a concern as people, in our demographic. So, and then that might be culturally construed as well. So I'm wondering if you could say something about how the kind of universalism in this kind of thinking versus the cultural specificity.
Yeah, so a couple comments. So in my wanderings, in general, I find that cultural specificity comes less into discussions around privacy than it does in considerations of fairness, for example. So while completely acknowledging that different groups and different individuals have different, demands or desires for privacy, some people really don't care about it at all. Some people care about it a great deal. I haven't encountered yet sort of systematic cultural differences on that notion. Whereas, when it comes to fairness, there seems to be, an upfront acknowledgement that different cultures might care about different notions of fairness. So for instance, in the United States, especially these days, there is great concern around racial disparities. In other countries where there's just considerably less racial diversity, there might be less concerns about racial fairness and much more concern about sort of religious discrimination, for example, okay? So in some sense, what I was kind of proposing as a drawback of fairness research, which is that there are too many definitions, and it's almost like you can program any definition of fairness that you want. But in some sense, since fairness definitely seems to have a lot of cultural.
So many terrific examples here, but I'll start with this one because it asks you something about the kind of cultural specificity in all of this. And it said, I'd be interested to know how cultural specificities are taken into account, if at all, in defining key terms such as privacy, since what is understood as desirable privacy may differ according to country, culture, or context, medical privacy versus, for instance, privacy in what I post on Instagram. That made me think too of the fact that, when I talk about these questions with my own students, they're certainly very interested in fairness, but they're not that interested in privacy. Privacy doesn't strike young people sometimes as quite as pressing a concern as people, in our demographic. So, and then that might be culturally construed as well. So I'm wondering if you could say something about how the kind of universalism in this kind of thinking versus the cultural specificity.
Yeah, so a couple comments. So in my wanderings, in general, I find that cultural specificity comes less into discussions around privacy than it does in considerations of fairness, for example. So while completely acknowledging that different groups and different individuals have different, demands or desires for privacy, some people really don't care about it at all. Some people care about it a great deal. I haven't encountered yet sort of systematic cultural differences on that notion. Whereas, when it comes to fairness, there seems to be, an upfront acknowledgement that different cultures might care about different notions of fairness. So for instance, in the United States, especially these days, there is great concern around racial disparities. In other countries where there's just considerably less racial diversity, there might be less concerns about racial fairness and much more concern about sort of religious discrimination, for example. Okay. So in some sense, what I was kind of proposing as a drawback of fairness research, which is that there are too many definitions, and it's almost like you can program any definition of fairness that you want. But in some sense, since fairness definitely seems to have a lot of cultural specificity, maybe that's actually a good thing. Certainly, I mean, as far as cultural differences around privacy goes, I mean, there's the usual claim that, the European Union and its citizens seem to care about privacy much more, and the GDPR is often held up as this model for privacy regulation, which I don't really think it is, for reasons that I won't go into unless somebody's interested. But on the topic of like younger people, for instance, not caring about privacy, I've sort of generally experienced that. But since I also, work with undergraduates and young people, and I actually am, for the third year this semester, teaching a course on exactly the topics of this lecture, but at a more technical level, I find that even students that are technologically sophisticated who previously didn't care about privacy, when they learn more, they start to care a lot more about it. So for instance, one story I like to tell, or one paper I like to often talk about or assign, is a paper from maybe 7 years ago from the Proceedings of the National Academy of Sciences, where what the researchers did was they went and got data only on your Facebook likes. So nothing about any declared demographic information that you put in your Facebook profile, nothing about who your friends are, nothing about the text or messages that you exchange with friends in your posts, just like the transcript of what pieces of content you have given the thumbs up button on Facebook. And these researchers showed that to a fairly significant level of statistical accuracy, that just from your like behavior, you could predict things like your sexual orientation, whether you are the child of divorced parents, your religious and political affiliations, your drug and alcohol use, and the like. And so, this is one of many examples where information that we freely offer in public forums that we think is innocuous might actually be highly predictive of things that we think of as quite private that we would never think about offering in a public forum. And when you show kids that, it often changes their mind about privacy.
Yeah, that is fascinating. That does suggest, right, that the things we give away that we think are not particularly worrisome can be put together in ways that we might not appreciate. Well, somebody else asked a question about the opposite, finding more stuff in the data, which is to say, how do we find all the subpopulations in the future data to check for unfairness?
Good. So if I'm channeling that question correctly, you might mean like, well, okay, I could ask for fairness by race, I could ask for fairness by gender, I could ask for fairness by religion. So actually, I like this question because I think one of the favorite pieces of research I've done in the last decade or so myself with colleagues here at Penn was exactly on this topic. And one of the themes of our book is that machine learning won't give you for free anything that you don't explicitly ask for, and it will not avoid behaviors that you want to avoid that you didn't explicitly instruct it not to avoid. And so, to give an example of that in the line of this question, suppose I train a machine learning model and I explicitly, kind of in the way that I suggested in the college admissions example, I demand that it be fair by race, by gender, by age, by income, by disability status, etc. So I list all those things. there's no guarantee that the model that results from all those constraints won't discriminate against disabled Hispanic women over age 55 making less than $50,000 annually. Because I asked for each of those constraints marginally or independently, I didn't ask for them in combination. And I learned in doing this work that there is a term for this phenomenon, broadly speaking, known as intersectionality, which I'm sure that many of you knew about long before I did, for exactly this kind of notion of overlapping groups, that people are members of many different kinds of groups. And so it turns out there are things you can do scientifically here. You can actually design algorithms that will not only enforce fairness constraints by the attributes that you list, but by kind of complex combinations of them, or even more complex functions of them. Again, you do still have, you can't promise everything, right? Like in particular, just to be clear, any machine learning model or algorithm is always going to make mistakes. Okay, so if this is the nature of machine learning. You're taking sample data from some population, you're trying to predict something, you have a finite sample, your model can't perfectly capture the world, you're going to make mistakes. And so if our notion of fairness is just differences in performance or error rates across different populations, if you let me look at the model that you trained and say like, okay, I'm just going to look at the subgroup of the population on which you make mistakes and call that like a subgroup, if you let me kind of overfit or cherry pick my definition of the group to be just exactly where your model makes mistakes, there's nothing you can do about that. That group will always have a 100% error rate by definition, which will be much higher than the overall error rate. So, you can't hope to protect kind of arbitrarily complex subgroups of people that have no kind of attributes in common other than my model made a mistake on them. But if you're willing to commit in advance to the attributes that you do want to protect, or the combinations of them that you want to protect, then we have some handle on how to do this algorithmically.
That's fascinating. So the intersectionality can be understood in a kind of algorithmic fashion.
Yeah. This has been one of the more satisfying pieces of work I've done, just because we did it as kind of this technical question that was quite challenging and interesting, and then we discovered that there's this whole notion in the social sciences and elsewhere that specifically study this notion, and so that was kind of a serendipitous project.
Because it's true that when you started talking about your pluses and minuses in your entrance to Penn example, you started talking about them originally around income, and by the end they were maybe proxies for race. But you could imagine the data would look a little different if you talked about it around race versus income, or some combination of the two might change the pattern.
That's exactly right. Yeah. And by the way, maybe one thing I'll say more about this is it's easy to sort of write down the algorithmic problem of being fair with respect to more and more constraints. The concern empirically is that the more constraints you enforce, just the worse your trade-off between fairness and accuracy. So maybe I can ask for a million fairness constraints, but the only way I can satisfy them is with a model that has horrible predictive error that we would never really want to use in practice. And so one of the interesting empirical things about this line of research is that it does appear, at least on many data sets, that you can actually ask for this much kind of richer notion of fairness, this intersectional notion of fairness, and still, find yourself within a model with appealing error.
Well, some people want to know more about the sort of, how do you make this all become a real world project as opposed to an abstraction? And they're asking in some ways questions about business. So let me read you one or two of these. Someone in our audience asks, but how will a capitalist system be willing to adapt or encode these algorithms if they don't maximize profits? How would you persuade them to do so? And there's another question along those lines that says, let me see where I can find this. It seems differential privacy depends on the amount of noise added by the company. Is there a concern companies could claim or advertise differential privacy, but add little to no noise? In other words, sort of some skepticism, it sounds like, about whether whether it's Netflix or Penn, will go this route?
Yeah. So on the second question, that could and has happened. Like one of the earliest uses of differential privacy was by Apple, and they used it in a very innocuous application, which is to gather statistics on app usage, right? So Apple, and especially its developer community, is very, very interested in usage statistics for different apps. Okay, and so are and app developers are, obviously. But they also know that that might be sensitive, private information, that I might, for instance, be embarrassed that I still play Bejeweled for 7 hours a week, for example. And so they proposed, like, well, we will, iPhones will upload usage statistics from my phone, but it'll add noise to it in a way that promises differential privacy. And after they did that, some researchers took a hard look under the hood at the implementation and the claims, and basically said, like, oh, you are not adding nearly enough noise to provide the privacy guarantees that you're sort of proposing. So these kinds of things, like everything, it's possible to get implementations wrong, to make bad choices about the details of implementations and the like. I think, maybe let me address the first question, which I think kind of had a slightly broader scope, which is if, as I've suggested, all of these enforcements of social norms will come at a real cost to adoption, like, revenue and profits will be lost. So like, why in the world, what's the path to adoption? So I think it's a fewfold. One is, I think, the sunlight is the best disinfectant is a big element of this, right? These topics are getting more and more scrutiny, right? And furthermore, right, one thing that's very new in my career in the last few years is kind of the rise of AI machine learning activists, as I might call them, people that really kind of view their role as watchdogs of this technology. And because a lot of these products and services where there are privacy and fairness concerns have public-facing interfaces, like like Google search or Facebook or APIs, like commercial APIs, like face recognition systems offered by all of the major cloud computing providers, there has arisen an ecosystem that's some mixture of academics, researchers, journalists, and the like, who do audits on these products and services and point out their flaws, right? So, even though I have a role at Amazon these days, it is not, it is no secret that Amazon's face recognition engine was kind of audited a couple of years ago and shown to have gender and racial bias by, by journalists and academics. So I think that scrutiny is a big part of it. By the way, mileage varies across them, but the big tech companies are actually very aware of the science that I described here. And in fact, many of them have large numbers of researchers and engineers who are thinking hard about implementing these things internally. So I think, so I think the combination of the companies starting to understand these technologies and realizing that, they could do this, that it might cost short-term revenue, but it might be good in the long run, especially if these things are getting more scrutiny, from watchdog groups and the like, is a big part of the equation. I think the other big part of the equation that I think will actually be the slower parts to evolve are laws and regulations, right? Because until you actually get precise about what is expected from a legal and regulatory standpoint, it's hard for companies to know what to do, right? And so, like, in my view, that, having spent a lot of time in the finance industry, like the finance industry in people, still think it's the Wild West there. But as an industry, the finance industry is extremely heavily regulated with very, very precise regulations, right? I mean, down to sort of the technical level where particular patterns of trading in the exchanges is illegal, okay? And there's sort of nothing like that in the tech community, right? So even though companies might want to do well by things like fairness and privacy. I think until our laws and regulations get more precise around what the expectations are, it's a little bit hard for them to know exactly what to adopt, how to adopt it, and how to make the choices. And the reason I think that part is going to take longer is just because of the relative kind of stasis of governmental agencies compared to industry, right? Like I think one of the things I'm suggesting here is that the staff composition of technology regulatory agencies needs to undergo a sea change before this can happen.
Interesting. That's really thinking about this. I mean, there's so many dimensions to this. It's a little mind-boggling for somebody like me to think about how much the choices, in some sense, made by computer scientists, whether in academia or in corporations like Amazon or Google, are in a sense shaping the choices we're all making without recognizing the sort of prior set of choices beyond them. So I'm going to ask you one last question because it's just rolled in, and I think it's a nice place to end, which is about sort of the public role in all of this. And I'll read you the question. The quest for the ethical algorithm seems to require greater vigilance, but also hyper-specialization. I was wondering what the role of the public might be in this new world of negotiations between ethicists and their clients, who would likely be either states or corporations. So I guess that means the rest of us.
Yeah, I mean, I'm very much aware in my work and my career and in the book that I wrote that, for better or worse, there's a real sense in which society has been delivered to the doorstep of computer science in the last 2 decades or so. And that, that's had great, there's been great things because of that, and there have been terrible things because of that. And, obviously one type of advice that somebody like me would perhaps irritatingly give is, the more you know, the better, right? The more technically you're informed, whatever level you have an appetite for, the better off you will be in understanding what's going on in the world around us and how to help. I mean, early in the book, we point out that, you would be forgiven for feeling queasy, that, 2 people like us are proposing that like the antidote to algorithms is more algorithms.
Yeah.
But there's, I think we are at that point. I don't think there's anything, unless we're going to somehow try to reverse the sort of technological society. I think, that's already past us. I do think, on a more perhaps productive note, other than telling people to go like learn computer science and machine learning and the like, I think the biggest gap in this whole picture are, kind of people in the middle, right? So, I'm an advocate for people like me, getting involved in policy discussions, getting involved in ethical discussions, getting involved in discussions with legal scholars and with regulatory agencies and companies and the like. But we need people from the other side as well, right? And that doesn't mean, people who think about these things at a higher level, like coming and being computer scientists. It means them learning it, like this diagram I showed of the trade-off between accuracy and fairness.
Right.
It requires somebody who is the stakeholder in the admissions office wanting to understand exactly what that picture is showing and what it means, okay? And they don't have to understand how that picture was generated or the details of all the algorithmic, effort that went into it, or have a PhD in machine learning, but they kind of do need to understand what the numbers on those axes mean and what the impacts of the choices that they'll make are. And I think the other big area where people like me need help is in thinking kind of about the, like in some sense, everything I've talked about here and we talk about in the book is talking about a very narrow piece of the overall machine learning pipeline, as I call it, or workflow, right? So, in something like criminal recidivism, like upstream from where somebody like me would enter comes the gathering of data from police reports and arrests and criminal records and prior convictions and failures to appear in court. And there are all kinds of things that are going on there that, that affect the data that one sees, right? When somebody fails to appear in court, it could be because they just blew it off, or because, if they appeared at that court date, they'd lose their job and not be able to support their family anymore. And like, by the time somebody like me gets that data, it's just like a column that says how many failures to appear. And so I think, if people want to know how they can help other than becoming, computer scientists, I think kind of just understanding that whole workflow, and also the downstream effects of, we build, again, for somebody like me, the job kind of ends with the predictive model, but then the predictive model is out there in the world making decisions that might inform, like parole decisions. And those obviously have serious consequences. And so, there are people at Penn who think about these things that I've been talking to a lot the past few years, that kind of think about, as they say, more the socio-technical system aspect rather than the middle piece of it, which is kind of the algorithmic part. And so I think, that is a very fertile and important area for people to play in.
Well, thank you. That's a terrific place to end, because this has been really enlightening for, I can tell from the questions, there's a big audience out there, and some of them are people with technical expertise and some are not, judging from the questions. And you've given us a lot to think about in terms of how all of us encounter this kind of new world of algorithms that's basically everywhere, whether we notice it or not. So thank you very much.
Okay.
And good night to everyone.
Okay, thanks, Sophia. Thanks everyone for coming. Bye-bye.